Again, welcome everyone to our Turing-Roche Tech-Talk series, which aims to share technical resources and knowledge to improve how we do computational-based work, I guess specifically in the medical sciences. If you weren't aware, the Turing-Roche partnership has been established to bring together researchers across academia and industry with the goal of better understanding patient and disease heterogeneity. Through this, they have several community scholars, which with different projects aiming to support this goal. As part of my project, I'm running this seminar series. And with that, I'll move on to introducing our speaker, Claudia. Claudia is a few years above me in the same PhD program, and she's someone whose work and approach to research I admire very much. Claudia has built a machine learning pipeline applied to placenta histology images, and her work has recently been accepted into Nature Communications. Her talk today will be all about how to write collaborative research code intended for adoption by other researchers. So without further ado, here is Claudia.
Okay, thanks for the introduction, Ellen. I'm excited to share with everyone today my tips and tricks and things I've learned over my PhD on writing good collaborative research code. So a little bit about myself. I'm a final term DPhil student on the Health Data Science CDT at Oxford. I work in the Nelica and Lindgren groups at the Big Data Institute. I originally studied an undergraduate in philosophy and then did a computer science conversion master's and then came onto this CDT. And I definitely have an interest in writing like easy to read and good collaborative code. I mostly write in Python. I've written in a few other languages, but what I talk about today should be applicable to any or most, I should say, languages. Maybe it's not applicable to things like Haskell, but Python and R, I think, are the languages most of us will be writing in, so it should be applicable to that stuff. Although don't ask me any specific R questions, please. I also co-taught the research software engineering module for the last few years on the CDT. And I wrote the histology analysis pipeline.py, otherwise known as HAPPY. As Ella mentioned it, we found out last week that it was accepted into Nature Communications. And yesterday I submitted the editorial revision, although I definitely have some fears that I'm going to get a reply from the editor saying, you didn't italicize this particular bit and we're not going to accept it. But fingers crossed there. And I'm going to be drawing on examples from this HAPPY code base because it is a collaborative research code base. It was originally written for placenta histology analysis, and we have this nice DALL-E 2 generated HAPPY cartoon placenta in the bottom right. But now it's being used in the group for other organ histology as well. But I want to start with a question. What is collaborative research code? And it seems obvious, but bear with me. I would argue that all research code is collaborative code. Even if you are not directly collaborating with someone else on a code base, you are always collaborating with your future self. I'd be curious to know if how many of you might have experienced this, but let's say you've written some code, maybe a script, or you've started a small project, and then you've stepped away from that code for some time. Perhaps you went on annual leave, perhaps you switched over to another project with a colleague, whatever. And then you've returned after some time and you've looked at your old code and you cannot make sense of it. What does this function do? Why are these things in that order? What does this number mean? Why is it 17? Where did 17 come from? I've done this. I've had lots of people tell me they've done this. In that moment, future you is not very happy with its collaborator, past you. So we want to take the steps to avoid this from happening. The second, more obvious form of collaborative research code is when there are multiple people working on the same code base towards the same end goal, which is likely to be a publication in our case. This is probably the kind of collaboration you were thinking about when you joined this presentation, but I've tricked you all into a coding lesson and you're very welcome. Then there is the less common case where multiple people are working on the same code base towards different end goals. So this could be multiple publications over a longer period of time. You could imagine a high-performing research group, for example, that focuses on a few core research themes, and they could develop internal tools and libraries that are useful to current members, but also future members of the group, and that can speed up the publication process. I think this doesn't happen as much as it could, but it could be very powerful when done well. And this is the kind of code that Happy ended up being, which is nice. Finally, I want to highlight that we are usually releasing our code along with our publications. So any future users of our code bases can be thought of as collaborators as well. I see this happen quite a lot, but if you ever look at research GitHub code bases with lots of GitHub issues posts, either that's a great thing because it means the repo is very popular and lots of people are trying to use it, but it could also be a bad thing because the repo is very hard to use. And every now and then I'll come across like a really great research repository with a method I want to use. I'll look at the issues posts and it'll be like, I can't install, I can't reproduce results, I can't use this on my own data, and so on. So that's a bit of a shame, I think. Additionally, we're seeing code being run as part of the peer review process now. So it's important for that code to be as accessible as possible. More and more journals are making their peer review files open source, and it can be quite interesting to look through them. I noticed this lovely snippet from a Nature Methods reviewer. Despite this, installation fails, which is very poetic, but also must have been terrifying to receive in your peer review file. Thankfully, many of the practices that I will be covering in the rest of my slides apply across all 4 of these collaborative cases, although I won't be touching on installation problems as environments and setup really deserve their own presentation. Right, on to the practices. The first practice I'll be talking about is documentation, and there will be really simple stuff like this. Broadly, there are 3 kinds of documentation. There's a README. The README will summarize the code base and usually will contain installation instructions and examples of how to use the main entry points into the code. So an entry point, if you're not familiar with that term, are the kind of files you'll normally be running. These are the files that you will say Python whatever.py with command line arguments, and these enter into the rest of the code base. So they're called entry scripts. So I have this example here from the public Happy repo, and you can see the entry scripts are cell inference, graph inference, and there's this little demo work through on the README to help somebody use these entry scripts. Another important part of the README is that it establishes the shared language and convention for the users of the code base to follow. So if you have a particular structure that you'd like other people who collaborate to use, you can lay that out in the README. This is quite important, this idea of the convention. Even if you don't do it with a README, if you do it with, I don't know, a group Slack or joint meetings or something like Notion docs, try to maintain a consistent terminology throughout your collaboration on a code base. You kind of define like a little universe that is your code base, and you all use the same terminology. And that's quite nice, and that can speed up collaboration and reduce miscommunication. Another form of documentation is a doc string. Like I said, this is fairly Python specific, so I apologize for that. But a doc string is a high-level description of a function or class or method that follows a particular format usually. There are a few formats you can use for doc strings. And the idea is that somebody can come to this bit of code and they can understand what the idea of this function is without having to read the whole code in detail. So I have this example here, also from the Happy repo, and it's a shortened example of quite a big doc string, which just describes one line of what this method does, a bit more detail about how it works, and then details about the individual parameters that you pass to this function as well. And often you can include types here, which will help somebody trying to use the code. A little aside, I use a nice replacement for argparse in Python called typer, which I strongly recommend people to look up. Just look up typer Python docs and read about it. But it forces you to put types into your entry scripts, which is quite nice. And then there are comments. And these are lines that are written directly in the code that explain individual lines of code or sections of code. So these are probably the kind of documentations that people are more familiar with. Good documentation is really great, but what's even worse than no documentation is incorrect or out of date documentation. So if you're going to write documentation, please keep it updated. I have this slightly contrived example of a function that normalizes some data. And you will see the name of the function and you can tell, okay, this normalizes some data. You'll read the doc string and it says normalizes the data using the min-max method. And it says it takes some data to normalize and it returns the normalized data. So you might just read this and think, okay, this function uses the min-max method to normalize data. But if you actually read the code, it uses the z-score method to normalize data. And maybe it used to use the min-max method, and then somebody decided to change it to the z-score method, and they forgot to update the doc string. So now a collaborator might come to this function, read the doc string, and think, fab, min-max method. They'll use this method thinking it's min-max the whole time. They'll write about it in a paper, and it will be wrong. So keep your documentation updated. There's this concept I've come across, which I've heard a few people refer to as write-only code. So in data science, quite a lot of our code can be boiled down to a series of data transformations. Even deep learning really is a series of data transformations. And there are very powerful libraries for doing these kinds of data transformations, like NumPy and PyTorch in Python. However, when we use these libraries, we write quite complex and hard to read code because it's a series of fairly mathematical, difficult data transformations. And I don't know how this feels for most people, but for me, it feels like it's the kind of code that you write it once, and while you're writing it, your working memory is completely full, understanding how each line works and how it fits together. And then you trust that it works, and you hope you never have to touch it again. But this kind of code is a nightmare if you do have to touch it again. So can anybody tell me what this function does? And I'm not going to force anybody to actually speak up and try to tell me, but it's so hard to understand. If we look through it a little bit, we can see, okay, there's a KD tree and we're querying the radius. That's easy to tell because those come from methods from a library, so they're nicely named and we can understand them. But if you look through the rest of it, okay, we're doing some kind of loop and we're filtering, and then we're doing another loop with unique, and then checking if there's a tuple, building R somehow, calling unique on R, deleting from our original data and getting a result. That's about as far as you can tell just from inspecting this function, but it doesn't really tell you how it's doing it, especially line by line. So how can we make this better? And this is what I would refer to as write-only code. You have a series of data transformations one by one that each could be quite complex. One way in which we can make this function more readable is to add line-by-line comments. So it's much easier now for somebody to come and parse this bit of code. I've not changed any of the actual code that runs apart from adding some print statements, but I've added a line-by-line comment. So now if I just hide my screen, bear with me. So now we can follow each of these lines and see, okay, we're dealing with coordinate system, we're doing a nearest neighbor search. Here is why we have these different checks. Once we get down to building the list, okay, we're taking the first element and we're removing the others from the original coordinates. So you can kind of figure out what's going on by adding these line-by-line comments. And when a collaborator comes to this, it's quicker for them to understand what's going on, or it's easier for them to ask the original person who wrote it what's going on, because they can refer to these actual human readable bits. The next practice I want to talk about is good naming. And this can refer to the naming of variables, functions, classes, directories, files, entire projects, and so on. It's a lot harder than it seems, but it's really important in computer science. It's so hard, in fact, that it's become part of one of the most well-known jokes in computer science. There are only two hard things in computer science: cache invalidation and naming things. But it's true, naming things so that others will understand them in that context requires some thought. So if we return to our previous example, you may have noticed that not only was it this condensed, hard to read code, it was very poorly named. Lots of single letter variables. The function itself was just called process. That doesn't tell me anything. So it doesn't help the reader understand what's going on. But we can even remove the single line documentation and improve the naming. And suddenly the function is a lot easier to understand. It's still write-only code, so it still takes some time to figure out what's going on. But for anybody coming to it, it's a lot easier. And again, now people can communicate this using human language. Like, so how is it that the unique duplicate indexes are formed? Or oh, okay, so I get some indexes to remove. Well, I know that np.delete takes an array and indexes, and it takes the indexes to remove, and it removes them from the original. So now you can think through this function a lot easier. So naming is really important. And then if you add on documentation, that can really help. The next principle I want to talk about is levels of abstraction. So the goal of abstraction is to hide details. For example, if we want to load an image, what might actually be going on in the code is that it finds this file and it opens this file and it reads the individual bytes in the file and it constructs this image object in memory, and then it returns that object to you. So let's say it's doing 4 things. If we want to load another image somewhere else, we would have to do these 4 things again, and that can be quite painful, quite frustrating. It's much easier if we can just say, I want to load an image. In a nutshell, that's abstraction. It's really straightforward. It's just packaging up individual things into their own concerns. So there's this principle called separation of concerns. You keep the concerns abstracted into their own little areas. We can also understand abstraction at different levels. So this is a rough schematic of the different sections of a file that trains a neural network model, train.py. The highest level of abstraction here is that this file trains a neural network, train.py. The next level of abstraction is if we were to follow the colors in this schematic. This file has some setup, it has a model loop, training and validation, and it saves some stuff. That's another level at which we can understand this code. The next level down is looking at each individual part. But each individual part has another level down as well. So if you want to figure out what's actually going on during training, you can jump down into the code and go down the level of abstraction and find the details. But the important part here is you separate out these different levels. So you hide the details until somebody clearly understands what's going on at this high level. And then if they want to know the details, they can choose to jump down into the next level of abstraction. So this is also referred to as the progressive disclosure principle. And it's not a programming specific thing. It's quite common in UI design as well. Like, don't reveal all the information to the user at once because that can be really confusing. If they click on a particular part, then you can reveal a bit more information, more details. It's just better UX that way. There's another common principle that abstraction can help with, and that's called the DRY principle. You might have heard of it. It stands for don't repeat yourself. So let's say you find yourself writing a script, like a simple analysis script, and you've written a function that helps in that analysis. And then you've written another analysis script, and you found yourself writing the exact same function. And then you've done it again and again. And you've started to repeat yourself, and you've sort of wasted your time a bit. And now, if you need to go back and change the way that function works, you have to change it in multiple places because you've rewritten it so many times, and the assumption is that that new requirement applies in all of these cases. But there is an opposition to the dry principle called the wet principle, which stands for write everything twice. Sometimes it's also called AHA, for avoid hasty abstraction, but I prefer write everything twice. I think people didn't like wet principle as a name because it also could stand for waste everyone's time, which is like the dry people attacking the wet people, and programmers are weird. But the idea here with the wet principle is you don't want to abstract too early, because it can make your code a lot less flexible. If you're trying to preempt all of the future requirements for your abstraction, you're probably not going to get it right, and then you're going to have to rewrite it or like tweak all the other things that go into it so they all fit into this like nice, neat abstraction you've made. So it can be quite hard to know what abstractions to do before you've written more of the code. So the wet principle says, if you find that you've written something more than twice, this indicates that you should add an abstraction. So yeah, I personally quite like the wet principle, but it can be quite hard not to just use it as an excuse to avoid abstraction. There's a fine balance there. There's a great quote here from Kent Beck, a good programmer. First, you learn the value of abstraction, then you learn the cost of abstraction, and then you're ready to engineer. So I think that nicely summarizes this issue with abstraction. There's also a great Donald Knuth quote about over-optimization is the root of all evil, something like that. So yeah, it's a fine balance. The next thing I'm going to talk about isn't so much a principle, but it's a tool that can really help with writing this collaborative, friendly code that we want. This tool is version control. Version control is simply a system for keeping track of a set of files over time. I'm sure a lot of you use Git as your version control system. But version control allows us to keep a record of all the versions of a code base and the way it changes, so you don't have to worry about losing anything. It lets you go back and run a specific version of code. So say you knew you ran an experiment on a particular version of the code base, and for reproducibility reasons, you can now go back to that exact version, exact way the code was, and reproduce your experiment. So very important in science. You can also pick any version of your code and have that be a new starting off point, and that's referred to as branching. And you can collaborate with people more easily. And I've included this reference for learning Git. There's quite a lot going on there in that reference, but it's a pretty good deep dive. In the interest of time, I sadly can't go into more detail about version control systems, but I have included a cheat sheet style slide for some useful Git and GitHub workflows. So if you're just thinking about using Git locally, it's this system where you have a branch. So for people who might not be familiar, you have a branch and you have a series of versions of changes to the code across that branch. You can make a new branch which copies the code and saves a record of it using git checkout-b branch name. You make your changes, you add your changes to be recorded using git add-a, so that preps them to be saved as a change. And then you use git commit-m with a commit message to commit those series of changes into a new version of the code. Say you've done that a few times. Now you want to bring those new changes back into the original branch, often called main. You would check out to main and you would merge that branch into the main branch. So now all of your changes you did in this branch are back into main. And now you can safely delete your old branch. This is quite a nice workflow, even if you're only collaborating with yourself. You have this main branch that's always working. You keep it clean, you make sure your experiments can always run on it, so it works for reproducibility reasons. You say you want to add a new loss function, and you know that while you're adding it, your code's probably not going to work. You make a branch, you name it based on this loss function, you make your changes, you do your preliminary experiments in there, and when you're happy with it, you merge it back into main. So main always stays nice and clean. Then there's GitHub, which is a distributed version control system. So GitHub is really similar to Git from a workflow perspective, except now rather than just having a local copy of your code, you also have another copy of your code somewhere else. And that would be on GitHub. So your local copy has this link to the remote copy, and it's called the remote code base. And so a really nice workflow, especially if you're working with other people, is before you start doing anything new for the day, git pull. This will bring all of the changes across all of the branches into your local space. It'll also merge the particular branch you're on as well, so you get all the new stuff. You can check out to a new branch. You can do the git add -a, git commit stuff, exactly like with the local workflow. And then when you're happy, you push your changes and you make a new branch on GitHub with git push. Sometimes if you just git push, that's fine. Sometimes it will tell you need to link it to the remote. You can do that with -u origin branch name, but it often gives you little instructions for that too. So it can feel quite hard at first to get the hang of Git and GitHub, but eventually it becomes like second nature, and it's really powerful because then you're not afraid to lose your work and you can collaborate more easily. Oops. So related to version control is the practice of code review. This is quite hard to do alone, but when you're collaborating with other people, I strongly recommend doing some kind of code review process. So code review is the process of reviewing the code before it goes into the main branch, is usually the easiest way to think about it. 2 eyes are better than 1, more eyes are better than 1. You might have made a mistake, you might have missed something, you might have, called that docstring min-max normalization when it was z-score normalization. And if you have a code review process, somebody else is looking at your changes, not the whole code, just your changes, and they could catch that mistake. This can be done asynchronously, so you don't always have to have meetings, and you don't always have to be, sitting next to each other doing this code review. You can use GitHub and a thing called pull requests to do asynchronous code review. Essentially, you get your changes in your branch onto GitHub, you make a pull request on GitHub into the main branch, and then you can assign your collaborator to be a reviewer. They'll get an email, they come and look, and they can see side by side all the changes across the code that have been made in this branch and that you want to add to the main branch. And they can leave comments as well. They can leave comments on the whole file or the whole commit. They can leave comments on individual lines of the code as well in GitHub. And then you can resolve and keep on committing, keep on iterating until both people are happy. Or you can have planned code review. It doesn't have to be this super systematic thing, although that is quite nice. So for the Happy project, we've been doing Happy Club, which is a weekly 1-hour meeting where everybody who works on Happy gets together in a room. We put some code up on the projector and we talk about the code, and we talk about how it fits in with the rest of the code base. Is it following the conventions? How could it be improved? How would it be useful to somebody else working on the same project? Is it a more shared bit of code? And so on. So this has been quite a fun thing we're doing, and this can work well when you're collaborating towards these different end goals, or if there are many collaborators and you'll get in the room. I appreciate that could be hard to coordinate. I'm just going to reiterate this point again, because I think it keeps things quite clean. Keep your main branch clean and never directly commit to it. In fact, I think at one point, GitHub added like achievements, badges, and if you committed into main, it gave you a permanent badge on your GitHub profile saying like you like to take danger or something. I can't remember what they called it, but they really called people out for doing that. So I think they removed it because people got mad, but it did make me laugh at the time. I never did get that badge. So keep your main clean, never commit directly to it. Make a branch for a new feature, even when you're just working by yourself. Work on the feature, either merge it into main when you're happy or make a pull request, review the pull request, and then merge it into main. And there's this visual representation of how that might look. The main is this line. It branches down. There are little comments. There's those little comment symbols. And when everybody is happy, you merge it back up into main. So in the interest of time, I can't go over everything that popped into my head when it came to good collaborative code, but I've included a special mentions list. So environments. You should keep clean environments, conda, virtual env, whatever, that you can easily reproduce. So I suggest maintaining installation instructions, step by step, exactly what you did when you first made that environment, so that you can reproduce it whenever you need to. If environments can mess up, so if you can easily remake your environment quickly on say, your compute servers, that's great. Also maintain files like requirements.txt files that make it easier for other people, collaborators who come to your code, to install your code. Another thing is packaging your code. Packaging your code installs it into your environment as if it's an external library. So it's really nice because that means you can now import it anywhere in your code and you don't have to follow this fairly difficult to understand import tree structure, can't go up but can go across and 3 down. Don't worry about that. Package up your code and you can import it anywhere. I can share some tools that help with doing that in the Slack. Testing, I'm sure you've heard about testing. Testing really deserves its own presentation, but if somebody wants to learn about testing, I suggest looking at the PyTest library. It's got a really nice UI for doing unit tests and integration tests. So I think it's a good place to start, but yeah, testing it deserves its own thing. Debugging, I strongly suggest learning to use a debugger. So if you've ever found yourself adding in print statements when you're running your code before and after something, what does this variable do? Because you're trying to figure out what's going on. That's a form of debugging. And that suggests you could use a debugger. So a debugger means you can add a breakpoint, which means the code execution will stop exactly at the point of your breakpoint. And then you can see what is assigned to each of these variables. You can run arbitrary code. It makes it much easier to see when you've got a problem. So I strongly suggest learning to use a debugger. Editors often have one built in, like VS Code and PyCharm, but Python also has a library one as well. Also, learn your editor. Whatever code editor you use, they are super powerful, and just try to learn some of their features. There's a steep learning curve here for sure, and I'm not saying everybody go off and become a power user, but for example, there are hotkeys that let you jump around your code. If I press Shift and I start typing the name of a file, it doesn't matter where that file is in my project structure, it will come up and I can just really quickly get into it. Likewise, I can use a hotkey to click on a function and I can jump down to that lower level of abstraction that I spoke about earlier. So let's say I'm at a high level and now I really care about how training is implemented. I can use a hotkey, click on training, and find out the full definition as well. And you can keep going too. So that's quite powerful. Also, they help with formatting, and they catch errors where they can. So you just end up breaking the flow of thought a lot less, and you naturally write cleaner code. Code formatters are related to this. They help maintain that consistency. If you make everybody use the same code formatter on a project, then you will know what you're reading, you will know what to expect. I really like Black as a code formatter for Python, and that's becoming more popular. Similarly, I suggest looking up style guides for your programming languages so that you don't mix camel case and underscores where it isn't the convention to do so. These things sound silly because they don't change the way the code actually runs, but it's almost priming, like brain priming. You expect that camel case means a particular thing. So when you go and read another library, you see camel case and you just know what that thing is. It's a lot faster. Where are we? Here we go. Oh yeah, delete ruthlessly. I'm really serious about this one, and it took me a while to get used to this. But if you have a script or a function that is just there and it's not being used, and you wrote it because maybe you'd need it, or you wrote it and you discovered you no longer needed it, delete it. Code bases can rot, You'd think they can't because they're unchanging, but they really do rot. And part of that is from scripts that are not used. You can also imagine a new collaborator coming to the code base and finding a bunch of scripts and not knowing which one is important, which one is actually used. So be ruthless in deleting and have faith that Git is recording everything just in case you need it, if you like to hoard like I do. Another one is learning to Google well. So there's a bit of an art to Googling for solving programming problems, but it's pretty unlikely that you're the first person in the world with your programming problem. So you can probably find a solution online. And actually related to this, a very recent development is using AI to solve your programming and Googling troubles. Of course, I had to mention AI. Even if you don't use AI for writing your code, and it's questionable still how good it is at that, it can really help you with understanding code. You can look at a collaborator's code, put that little snippet into something like ChatGPT and say, please explain these bits for me, or add line-by-line comments to this code. I actually gave it that function process that we were looking at earlier with all the bad variable names, and I asked it, add line-by-line comments to each snippet, and it did it really well. I was quite surprised. It can also reformat your code for readability. You can use it to discuss ideas, plan your future. So only slightly kidding about that last one. But yeah, I use it a fair bit and it is really helpful. And enjoy it. Take pride in your code. Coding is actually a creative endeavor in a way. It's architecting and it's a bit of a puzzle. And it can be really satisfying when you end up with nice looking, readable, and reusable code. Before I finish, I just wanted to say that if you take anything away from my presentation today, or you take anything away from programming books and blogs and talks, or from reading good open source code, is to learn a few key principles and practices and to try and be consistent and disciplined in your application of them. And it's not easy, and I'm definitely not perfect at this. But John Carmack, who is widely considered to be one of the best programmers, defines engineering as such. Engineering is the disciplined production of technology. Thanks very much.
Great. Thank you, Claudia. That was a really good presentation. It was engaging, and also I think I definitely learned a lot. So I hope other people did as well. Now we might move on to questions, or even if people have comments or things that they maybe use and want to discuss as well. You can either maybe put your hand up or just post in the chat as well, and I can call on you perhaps. Sarah, I see you have a question.
Thanks. And Claudia, this was awesome. I feel like I related to so much about what you were talking about. And yeah, I'm excited to be able to share this. I'm a data scientist at Roche. And I had a question that was a little bit related to the environment, which you touched on towards the end, but also a little tangential to that. So I code a lot in R. There's a really useful suite of libraries in the tidyverse, which are used for data wrangling, manipulation, and they're kind of constantly updating over time. And so often when I'm collaborating with people, if I've written sort of a specific installation of a package internally and they go to install it, certain functions could be deprecated based on which versions I have and they have. And that's why it's important to sort of keep the environments very tidy and reproducible. But aside from that, there's sort of a camp in, I think, the computational group that believe you should reduce dependencies on external libraries as much as possible. And so code more in base R, for example, so that your code is not just sort of a mashup of libraries that can be constantly evolving. And I was just wondering what your philosophy is on that, and if you have any best practices that you've used.
I can't speak for R really, and it might be slightly different in that the zeitgeist in R might be slightly different, but I would say Well, I'll answer the reducing the amount of dependencies. I think there are some dependencies that are so extremely useful, like in Python, NumPy, PyTorch for doing the deep learning stuff, that there's no point to go off and rewrite some of the stuff that's in there. However, I also wouldn't try to find a dependency if there's a fairly simple, like, base Python library implementation of that. But I think really you shouldn't be afraid of having dependencies as long as you can easily make the environment that fixes the versions of those dependencies. Or you can have like multiple environments with different versions, as long as your experiments work with all of them. Yeah, I guess I'm not anti-dependency, but I know that in some languages, some dependencies add a lot of overhead, and you want to avoid them in that case. I know that web dev is a lot like that. Yeah.
Yeah, thanks.
So one thing I would add is the way I deal with installation and environments and dependencies is having a make file. I really like make files, and that works across languages. So that means you don't have to just use pip, but you don't have to just use conda. Sorry, it's very Python-specific examples. A make file will sequentially do your entire installation and fix the versions as well. So that really helps.
Yeah. I like snake-make a lot. Yeah.
Okay, thanks for the question, Sarah. We also have one from Manish. See?
Hi. Hi, can you hear me?
Yep.
Yeah. Hi, Claudia. Yeah, thanks so much for the presentation. It was really good. The examples you gave, like, kind of debunked a lot of sort of insecurities I've had during my own coding journey. So it's really, really good. So my background is mainly in quants and like the subset of like data science and research there. Is there any inspiring research projects that you could recommend, like looking up on GitHub or that you've used throughout your own PhD?
So actually for the Happy repo, for the way I structured that project, I used Meta's Detectron-2 GitHub repo. So this is fairly specific to deep learning, but they had this structure where they made Detectron-2, which is this kind of deep learning model, and they released their paper along with it. And then they had a directory structure called projects. And within projects, other people could come and add code that worked with the entire engine of Detectron-2 and make a whole publication just in that /projects repo area. So I used that as inspiration for making the Happy repo. Otherwise, I think there are examples online for different domains. So there are, again, I know mostly about the deep learning stuff because that's what we teach as well, but there's like good project structure for doing MNIST, but you can then use that project structure for a much bigger project as well. So just Google like NICE, or hard to recommend to say just Google this because you never know what you'll get. But there definitely are nice repos out there. Or if you want to go really deep, honestly, looking into the open source code of some of these big libraries like PyTorch or even base Python, and just jumping into the code and seeing how they define things and how they do things, that can be really nice. So if there's a library you really like using, look them up on GitHub.
Yeah, that's interesting. Yeah. Thank you so much. Yep.
I also see there's kind of a question in the chat which says, any resources to learn about virtual environments in brackets in Python you could share?
Ah, interesting. So this is more, environments is more popular than I thought it would be. Yes, there are. I will share them in the Slack after this. Annoyingly, with Python specifically, the recommended way to do like project setup within your environment is constantly changing. So it used to be have a nice setup.py and pip install -e dot, and that will install all your packages in your environment. But now that's not the recommended way to do it anymore. You use anyway, I can't remember the name, but I'll link the different recommended ways to do it. With virtual environments specifically, I tend to use Mini-Conda over Venv, in part because that lets you install a sandbox version of Python. So for a compute cluster, you can use Conda, install your specific Python version and all your requirements using pip in that environment, and then you have your nice little area that nothing else can interact with and touch. So that's why I would use Conda over virtual environment. I'll share some resources. I need to remember to do that.
Okay, if anyone else wants to ask a question or comment, now is your time. Okay, thank you all very much for coming, and thanks again, Claudia, for that brilliant talk.
Thanks for having me.